So, um, good day. I will start with the design process for our steel design. So, let's take into consideration the design of a beam. The summary of the procedure involves first, we have to determine the design actions, that is, the shear force and the bending moment at critical points along the beam based on the factored load. Then, we will now select our section, maybe a universal beam or a universal column based on the required moment capacity. Then we now classify this section. Is it going to fall under plastic, compact or semi compact or slender? So if you say class 1, that's plastic like that. Class 2 is compact. Then we now move to the shear strength. We check for shear strength and we verify that the design shear force does not exceed the section's shear capacity. If it is unsatisfactory, then we go back and select another member again. Then we check for bending resistance and then we check for deflection. So whichever one that fails, we have to go back again. So we now check for the web bearing and the buckling. We assess the web resistance to bearing and then buckling at support and under concentrated load. If it is unsatisfactory, then we provide web stiffener. Then the last one is we check for lateral torsion buckling. Then we evaluate the beam stability against lateral tension. So let's go to the example of the procedure. I said the initial section selection. I said for initial section selection, we look at is bending under critical mode of failure, and then we must make sure that our design moment does not exceed the moment capacity. Must not exceed the moment capacity. What I mean is that if the moment exceeds the moment capacity, that means the member will fail. So the design moment must not exceed the moment capacity of that particular member. That is, if a member is if the member, that is the steel itself, it can carry maybe 20 kilonewton meter at its maximum, and that as its maximum capacity, then the moment from the loading should not exceed that moment capacity. So let us for a steel section, the moment capacity is given by MC equals to Py dot S times S. Now, this our Py, that's our design strength that we're looking at for, and it's the use strength of that steel. And the S is the plastic modulus of the section. Now, when both equations are combined, then we must have that our S must be, that is, our plastic modulus must be greater than our M over Py. So this criterion can be used to select our universal beam or universal column sections. So the strength classification, I said we have S275, where 275 is the use strength of that particular steel, and we have them in the areas number which I have explained. Now let us go to the design proper. I will be going forth and then I will show you what each one entails as we design with a sample. Now let us say we have a simply supported beam with a span of 8 meters, and it is fully laterally restrained with nominal torsional restraint as support. It supports a uniformly distributed catalytic dead load of 7 kilonewton per meter and a uniformly distributed catalytic imposed load of 8 kilonewton per meter. Now we want to select a suitable universal beam or universal beam section that will be able to satisfy the bending and shear consideration. Now let us say we have let's say this is a car porch or something like that, and this is the loading on the particular member that we want to design for. The first thing is that we must know the weight of the load that is applicable on top, which will help us to know the maximum bending moment that particular load will exhibit on this particular structure. So now we'll calculate the reaction, which everybody should be able to do by now. So let us see the first procedure: design bending moment and shear force. How do we go about that? We get the total loading by using 1.6 to multiply our imposed load and 1.4 to multiply our dead load. As you can see here, we have 2 imposed load here and 1 dead load. So this one is for the first imposed load, the point of why this one is for the uniform distributed load, 1.4 times dead load for 1.6 times QK. So if we were given 8 meter span, 8 imposed load, and the other 7 7 dead load, 8 imposed load, and second imposed load of 35 kilonewton at mid-span. So when we calculate this, we have a value of 236.8 kilonewton. Now, after getting this, we have to distribute the load at this load. Since it's only having 2 support, we have to know what load this one will carry, what load which one will carry. So by the time we divide it by 2, because it is symmetrically loaded, had it been this one is at a distance here, then we have to calculate and get the actual load that will be sent here and the actual load that will be sent here. But since it is at the centroid, we just divide the load by 2 and believe that it's going to carry half of the load. Each support will carry half of the load, which is what we have here. Then we now design the bending moment. The bending moment, the maximum bending moment for uniformly distributed load is WS square, while for a point load, the maximum bending moment is WL over 4. So that's why we are adding the two together, WL over 4 plus WS square over 8. So by the time we put our W, which we already know, this is our W, which we already know, that because the action of, we have uniformly distributed load and imposed load, so we treat them separately. The one for uniform distributed load will be separate, while the one for imposed load, for point load will be separate. So now this one will be used for the point load, while this one will be used for the uniformly distributed load. So if you do your calculation very well, or if you look at it, when I was doing the calculation here, this is the one for the uniformly distributed load. That's what we have here before we multiply by the span, and this one for the point load, which is this. So that's exactly what we're going to use here. Where we have this W for the point load, we use this. Where we have W for the uniformly distributed load, we are going to use this particular one. So here we calculate our central bending moment, which is this, and then we arrive at 292.8. Then we calculate the shear and the moment. We already know that, okay, since our W is this, and small w for the uniformly distributed load, for the point load, our reaction at each support, then we know the span and we know the mid span. So we want to generate equation for S, which will help us to know the shear force and likewise the moment at every point that we're going to touch in that particular beam. So this one is useful for drawing bending moment diagram. When you just sort it, for instance, this one, if this S is less than equals to 4, that it will be applicable from here to here. Now if I put let's say I put X to be at 0 now, what is R? 118.4 minus 22.6 times 0, whatever it will give me, because 0 times this will give me this, so I will only have R here, which was 118.4. That's what I have here. Now if I change this one to 2, change this one to 2, I will start and substitute it, I will have the value likewise for every other one here. So this equation is what we that's the equation that is showing what happens on this beam when S is less than 4, and when S is greater than or equal to 4. This is the one that is applicable. So you can substitute that and check. This is the final bending moment diagram and the shear force diagram. Now, since we know the final bending moment diagram and the maximum bending moment diagram, and the maximum bending moment is 292.8. Now that's what we're going to use here, 292.8 all over our PY. This PY, that's because we have been told that we're using S275 steel member, S275. So its use strength is 275. That is why we're having this 275 that we're using here. So this 275. So by the time you do this division, you have SS will be greater than this. Now when we now calculate, when we get this is the one that will serve as a basis for us to know which member we are going to select from all the numerous members in the steel table. Now for this particular one, we have 3 member that is closer to this particular range. If I may check, let me quickly see if I can see if I can get a, let me see if I can show you a table of the steel table so that you understand what I mean. So let's see steel table. This member 457 by 152 by 52 universal beam. So we'll go to our steel table, which is this 45. I think it's 45 457 by 152. 457 by 152. Then the last one I think is 52 by 52. Now let us look at its properties. All these values here, it is from the steel table that we will select them. All these values. So when this is what we have, so we have to look for something that is higher than this in the steel table. So that is where we got this all this member size that we are selecting. So for this one, we look at the member by 52. So what do we have there? We said we have I think 1060 something. So firstly, you will look at the members you have. Do you have the section modulus here? So if you don't have the section modulus, you go and look for where you have the section modulus. So it will help you to know where you are looking, where you are looking at. Now you can see here, this is exactly what you are looking for. So we look at that member here. This is the one we are looking for here. So now you can see the section modulus of what we have here. The plastic modulus. We have along the x-axis, we have 1100 here. We have 1290 for this one. Let me see what I have in this other side. 1090. So though I don't know whether this one is the latest one that I'm using, but 1090, I think this one is okay. But the old one I have, this one is 1090. So I'm selecting something that is higher than the initial 1064 that I have. I can't take anything less than this. I'm something higher than this, so we can take either this or this. So let us see 406 by 178 by 60. 406 by 178 by 60. So we look at this one again. It's 1200 now. So those ones are higher, so we can always take those ones. So I think this one is having less than 10 units less than what I have there. But now you will understand what I mean. So we will just select either of this member. Then any member that we select, it has its own properties that we always take their, like the, let's say for this, for instance, this particular one, or let me use this one that we use. This one, the first table that we were checking the other time, which is this, the by 52, which is this. Here we'll be able to see the properties like the D, the width of the section, the T, all these values. I will show us where we will be making use of them as we proceed. So let us continue. So the next thing is that we selected this particular one. So we will now look at the flange thickness, which is T, from the one I showed you just now. The flange thickness of that member. What is the flange thickness by 52? Is 10.9 here. This 10.9 is less than 16, so we are still good. It's less than 16 mm. So then we look at its PY is 275 as from table 4.3, and E equals to this over this, then raised to the power of half. So if you divide 275 by 275, you have 1. Square root of 1 is 1, so that we have 1 for E. So now this flange classification is under our BS code. We will check B over T. What do we have at B over T is 6.99, which is less than if we use the normal 9E. Let me see the table that we okay, I think I have it. Maybe I have it in the notes. The table that I'm trying to select is the one we'll check for the, okay, this is what I'm trying to apply. This Eurocode zone, this for BS, this table. The table we're trying to look at B over T, whether it's less than or equals to 9E that you are seeing the other time. So since it's 1, B over T is still less than or equals to 9. Definitely this is under plastic section. So the way we do it, we first check this before we go to this, If it doesn't satisfy this condition, then we'll check for this. That means we'll design as a compact, and if it doesn't go for it, we go for the other one. So for this particular one, I think we are good. We can proceed with our calculation. So what we will just do is once the conditions are satisfied, then we check for the shear strength. If it is satisfactory, if it is unsatisfactory, we return to 2. And for that one, we check our D over T, which is 53.6 in what we have for the member. So let me check the member again. D over T is 53.6, as you can see here, so which is less than the actual one in the code, which is 70E. So that means shear buckling is not, it doesn't need to be considered. So had it been it is greater than this, then we have to consider shear buckling. So we check shear capacity again. The formula for shear capacity is this. Now, how do we get this AV? This is the formula for getting that AV is T times D. This AV is T times D in our code. So by the time you put the value of T and D that we have in the member selection, then you're going to have this. Then we have this particular shear capacity. Now, our maximum design should be less than 0.6 PV. So 0.6 PV is this. So that means it's under, if this condition is satisfied, that means it's under low shear. So our shear is, since our shear is this is our this is the one we want to check against. But if you can recall, our maximum, our limit, our load that is support, that shear load at the support the other time is 118.4. So we check this against this. So this is less than this, so that means we are still good. So this times this is this, which is this. Since this is less than 1.6 times this is a low shear load condition. Then we check for bending resistance again. All this design, they have different procedure, they are step by step. You have to follow each step one after the other. Now we want to check for a class 1 section under low shear, the moment capacity m is equals to PYS. We already know how we got this, we have this value. Then we are going to check whatever we have, make sure that it's less than or equals to 1.2 this. So this is less than this, that is, this must be less than this. So if that condition is satisfied, then we are okay. Then the moment due to imposed loading, we already know this one. The extra moment due to self weight is we want to calculate the self weight, that's WL. Now this steel member, we have the steel member, this 52, that's the weight of that particular steel. So that's the mass of that particular steel that we're going to use in this calculation. So for this, to get this, we just do the same thing, you know, weight is mass times acceleration due to gravity. So the weight is like the force. So applying factor of safety times the force, then we have this. Since we know the mass here, easily we can say, okay, 52 is the mass. Please don't forget this value. This is where you get the mass. This value, the last value here, that's the mass. So that's where we're using here. Mass times acceleration due to gravity will give us weight times 1.4. So this is the weight of the steel member itself. So we add this weight with the actual total weight we have, total imposed load we have the other time. So the sum of the two is this. The section is switchable, but if you can look at it, it is very close here. So at times you have to use another member because it's very close, but because for explanation purpose, since it's less than, I will still go with it. But in case it's greater than, you have to go and select another member. Now we check for deflection. Now the deflection, we always check for the deflection under unfactored imposed load. Under unfactored imposed load, that's the condition to, that's the criteria to check for its deflection. Now we have our Q with the uniform distributed load at 8 and a point load of 35. The other one is dead load, which we are not considering because we are only considering imposed load. So if we use this one now, we calculate using the formula 5WL over 4 divided by 384, as I showed you last time. Then we get the value out. This one will give us the deflection, which is 18.3. Now there's a recommended maximum beam span over 360, which is relevant for the deflection. So we check this value with the limit. This limit is since our span is 8 meters, we divide by 360, we have 322.2. And now since this one for other beams is this or this, which is 40. Now since this is less than the maximum deflection that is expected, then we are okay, the section is okay. For further check to be performed, we can check for bearing capacity and buckling later. So the member that we're still considering is this particular one. So if there's any question on this, you can always drop in the comment section. I will go to the tension later in other video. Thank you.